Yes. All right. Announcements. Homework number 3, I just posted a couple hours ago. That's on short fiber composites and particulate composites. 3 questions. They're all like semi-related, so kind of a fun homework in my personal opinion. Maybe you don't think so at the end, but hopefully you don't cry too much. That's going to be due on Tuesday, this upcoming week. And you have everything ready to tackle that. So everything on kind of the back end of the micromechanics notes is going to be able to help you through your short fiber and particulate composite materials. Okay. So let's move on. I've uploaded a new set of lecture notes on anisotropic materials, and we'll start in on that new material today. So let's do that. Get rid of this, bring up this, do this in the thing, and here we go. Okay, away we go. So when we did micromechanics for back to continuous fiber composites, we kind of made some assumptions, and we talked about basically the moduli of the material in like the one direction, the two direction, etc. Okay, but that would rely on the assumption that we have fiber generally one direction in the composite, which is usually not true. And it would also imply that we would only potentially care about the modulus in the one and the two direction, which is also not true, because you could potentially load off axis, and maybe we want to calculate like what would the modulus be if we loaded in a different axis that wasn't necessarily aligned with the fibers. Okay, so I'll say the micromechanical models that we've started with so far are useful stepping stones, but don't paint the whole picture. And we sort of made a lot of assumptions to start, and now we're going to sort of draw back some of those assumptions and be much more general with our pursuit moving forward. And we're going to be very general in the fact that we're going to say that we have some material now that behaves on like a macro scale, and its properties are different in every direction. Okay, so let's put some words to that. Anisotropic materials. Generally, let's do an intro. Okay. Now, when we did the micromechanical models, we sort of assumed that we had unidirectional composites. The early micromechanical models are nice. But assume unidirectional composite. Meaning all fibers in one direction. And loads only in 1, 2, or 3 direction. Important. Okay. So what we want to do over the next probably 2 weeks is talk about how can we define the elastic modulus in some arbitrary direction with some material that behaves differently depending on the direction you're loading it. Okay, so that's what we want to do over the next few weeks. Okay, in reality, composites have fibers in multiple directions. And are loaded in complex ways. Not just the one direction, not just the two direction, etc. So what we want to do is we want to generally talk about anisotropic materials and how they behave. So we'll break down Okay. I will make the last comment here that we're going to be pretty mathy over the next week and a half. And that's because we have to sort of lose or strip away what you might naturally think of an isotropic material, same behavior, all different directions, and talk about potentially loading a material in a variety of different ways and a variety of different axes. And that's going to require heavy amounts of matrix math that really is going to look a little complicated and be looking nasty on the paper, but hopefully we can get it to a simplified state where we can actually start working with it. Okay, so a lot of math to come. Buckle up, wear your math pants, etc., and let's get fun with the math here. Okay. So before we dive in, let's do some general definitions. All right. Which will be important for us as we move forward. All right. Isotropic material. This is a material with properties that are independent of orientation. Okay. It's like any aluminum, steel, etc. that you're probably familiar with, whether I load it, this way, that way, whatever, behaves the same in all orientations. And this is the basis for like your ME2004 class, your ME3005, basically everything that you've seen up to this point. All right. We need to describe what a plane of symmetry is. Okay. Plane of symmetry is a plane with an outward normal that we could sort of rotate 180 degrees around that outward normal and still have the same properties of that material. I'll show an example in just a second. Okay. 180-degree rotation around an outward normal to that particular plane. If the properties are generally unchanged, you're good to go. Here might be an example. Okay, if we've got some composite with fibers in it that are running this direction. Right. And we generally know this to be like the 1-2 plane. All right. Here, the 1-2 plane would be considered a plane of symmetry. If I rotated this thing 180 degrees about the 3 axis, it would still look the same. Right? So if I loaded here, for instance, I rotated 180 degrees about the 3 axis, it still looks the same. Okay. All right, plane of isotropy. This is a plane about which any rotation about the outward normal leaves the properties unchanged. I'll try to keep my wordage the same. On which any rotation about the outward normal leaves properties unchanged. An example might be if you were looking at a unidirectional composite down the one axis. So let's say this is like the 2-3 axis of a unidirectional composite. You'd be looking at this. Okay, this is sort of what you would be looking at. Down one axis. All right, the idea here is that in this particular plane, any rotation about like the one axis, right? If I rotate this plane about the one axis, it's going to respond no matter how I load it. So the idea is if I load this way, if I load this way, if I load this way, whatever, it's more or less behaving the same in all sort of directions. Okay? So, we know that generally these unidirectional composites are not isotropic as a whole, but we could consider this 2-3 plane as a plane of isotropy, because if we load it sort of in this 2-3 plane, it behaves the same ways in all directions. That's why the calculation for like E2 in unidirectional composites is the same as the calculation for E3 in unidirectional composites. It's the same idea there. All right. Next, general anisotropic material. This is a material with no planes of isotropy or planes of symmetry. All right, meaning you have no symmetric behavior. It's hard to like draw this, actually. Not many materials in the world exist this way. Maybe like you could make an argument for wood, kind of, okay? Because the granular structure is sort of different at every location. You might make an argument for that, okay? But it's very difficult to actually find this in reality, all right? Most materials have some sort of symmetry or isotropy or something like that that you can latch onto. All right, most materials. It's really hard to find a material that generally doesn't have this idea. Okay, orthotropic material. Orthotropic material is a material with exactly one plane. Well, one plane. It has two different definitions. Let's go with the one that I have in the notes. 3 mutually perpendicular planes of symmetry. Um, okay. Uh, a unidirectional composite would count. All right. So if we went back up here, here's the 1-2 plane. If we rotated 180 degrees about 3, we'd have the same property. If you're looking at the 1-3 plane, it would look exactly like this. Rotation about 2, 180 degrees, completely unchanged. And then here, if you're looking down the one direction and you rotate 180 degrees this particular object, you would end up with the same properties. So a unidirectional composite counts. All right. Let's talk about principal material axes. Principal material axes are these three mutually perpendicular planes of symmetry of an orthotropic material. So it's basically those planes described up above for this orthotropic material. Okay. Finally, transversely isotropic material. A material with one plane of isotropy. All right. A transversely isotropic material must be orthotropic. So it will be orthotropic by default. You cannot have a transversely isotropic material without orthotropic behavior. An example is a unidirectional composite. Okay, definitions, exciting. Okay, we just had to get those out of the way. Okay, definition's gone. Okay, let's get back to math because that's what we know. All right, forget this English stuff. I like writing in math. All right, one other kind of precursor we need to get out of the way is reviewing your 3D stress element and also talking about indicial notation. Let me ask a question. Have you guys talked at all about indicial notation in any of your classes? If I say that, do you know what I mean?
No.
No, I hear in the earbuds. No, the audience looks confused. Okay. So let's first talk about a review of your 3D stress element. I have a comment in the chat. My hand hurts, says Alex. Okay. Go to the closet, get some Aleve. We'll wait for you old man. Okay. What's that? I don't know. Go to the medicine cabinet, okay? Or wherever you keep your drugs. Not those drugs. Preston, your mechanics and materials teacher did not skip this. Okay. I know because it was me. All right. Review your 3D stress element. So at any point in space, stress given by taking this class. Okay, just kidding. By things like stress in the x direction, sigma y, z, tau x, y, shear stresses, tau x, z, tau yz, tau y, tau x, and tau zx. Your 9 stress states, normal stress and shear stress. All right. Can be drawn on what we know as the stress cube. Thanks, old man is ready now. Okay, good, Alex. There's no crying in composites. I'm just kidding. There's lots of crying. Wait till the test. Hopefully you saw this stress cube in your mechanics class. It's a representation of stress at a singular point with 3 mutually perpendicular points. Where each time you make a cut, you can calculate 1 normal stress and 2 shear stresses. So if I cut through the YZ plane, I can calculate sigma x, and I can calculate 2 shear stresses here, which are tau on the x face in the y direction, tau on the x face in the z direction. If I cut in the xy plane, I can get my normal stress in the z direction. I can get these 2 components of shear. Here, this would be tau on the z face in the x direction. This would be tau on the z face in the y direction. And if I cut on this top surface, I can determine the normal stress in the y direction. And I also have resulting shears. Here, this is your shear stress on the y face in the x direction. And here, this is your shear stress on the y face in the z direction. Okay, those are 9 states of stress that could exist at a particular point. Stress cube, not stress ball. Yeah, you guys probably got stress balls at home too. After I do this lecture, I'm going to need one. So in matrix form, we typically write this as your stress sigma ij in the following way. Got your normal stresses in the diagonal. And you got the shear stresses in the rows. Okay, hopefully you've all seen this before. I know this is the first time I've seen it. All right, so here, this like sigma ij, this is like a form of indicial notation, all right? Where this actually represents 9 values. With I and j both ranging from 1 to 3. We understand this? Okay. Or if you want to think about it in the previous example, it would be x, y, z. All right. 1, 2, 3, x, y, z. Michael Jackson approved. A, B, C, easy as x, y, z. Exactly. Okay. So we'll stick to like the 1, 2, 3 for now, but understand that it basically means the same thing. We'll work with 1, 2, 3 in this class. All right. And that's because by definition, composites usually have like a one direction along which the fibers act. And so composite people tend to like the 1, 2, 3 sort of idea. All right. Now, you have seen sort of an introduction here to what is indicial notation, and you didn't even really know it. Okay. So this concept of this idea of like sigma ij, where it could be sigma 1, 1, 1, 2, 1, 3, 2, 3, 3, 1, et cetera, et cetera, et cetera. This is an introduction to what is known as indicial notation. This is the basics of indicial notation. Okay, where we have something like sigma ij with I and j going from 1 to 3. Could do something similar. With strain at a point. Where something like epsilon ij represents the 9 strain states. Okay, this is how very high level mechanicians present their material, right? And they do it this way because it's a lot simpler and a lot faster to represent multiple equations. And I'll show you what I mean by that in just a second. So we're going to have like some arbitrary stress state at some point of interest in our anisotropic body. All right. And we want to be able to describe that stress state quickly. And we might just say that it has an arbitrary stress state on it, sigma ij. That is supposed to represent to you that that particular point has 9 states of stress, and this one variable is meant to represent that. Instead of writing 9 different things, I just write one thing, and you understand what it is. That's the whole point of indicial notation. Okay? A couple of other things that you'll see with indicial notation. Tricks with quotes of indicial notation. If you've taken a linear algebra class, you've talked about the trace of a matrix. Who remembers the trace? It's not when you like put a, you put a stencil down on paper and you copy it over. No, that ain't a trace. Okay. If we want the trace of a matrix, you add diagonals. All right. You add the diagonal terms together. An example might be the trace TR of sigma ij is sigma x plus sigma y plus sigma z, or what we might say sigma 1 plus sigma 2 plus sigma 3. Okay, that's not that hard to understand. All right. The other thing we might want to do is to be able to quickly represent the identity matrix. And with indicial notation, that is known as the Kronecker delta term. I'll spell it out for you. K-R-O-N-E-C-K, Kronecker delta. Okay, this is a indicial form of the identity matrix. That's typically denoted with the lowercase delta. Delta I-J. Here for us, that would be the identity matrix. If I and j go from 1 to 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Binary solo. Okay. What is the point? Who gives a rip? Why do we care? Okay. Well, we care because we can, like I said, represent some of our well-known equations relatively quickly using indicial notation. Let me show you what I mean. Here is the full 3-dimensional Hooke's law using indicial notation. Are we ready? Epsilon ij. 1 on E. This is specifically for isotropic material. Sigma ij minus nu times the trace of sigma ij Kronecker delta minus sigma ij all closed. That is 9 equations. Believe it or not. Blown away. Okay, let's investigate one of these situations. Let's look at, for instance, I and j equal to 2. All right. Then we have strain 2, 2, or just the strain in the 2 direction, equal to 1 on E times sigma ij, which here is stress 2, 2, or just stress 2, minus nu times the trace of sigma ij. Okay, that is sigma 1 plus sigma 2 plus sigma 3. It's your trace sigma ij. Multiplied by the Kronecker delta, entry ij. So the 2, 2 entry of the identity matrix is the value 1. Minus sigma ij. So this will be minus sigma 2, 2. All right. You simplify this bad boy. We can sort of drop the second 2 in these guys. It's the same thing. You simplify this thing, you'll end up with 1 on E times sigma 2 minus nu sigma x, sigma 1 plus sigma 3, which is the 3D form of Hooke's law in the 2 direction for any material. All right. So this is one of the 9 equations that comes out of that indicial notation. All right. Yeah, exciting. All right, you could do the same for all the other 9 other entries and whittle them down. You would find the equations here on the left-hand side of this particular slide. These equations here, I'm showing 6 of them. We're assuming that these bottom 3 are redundant because of tau xy equals tau yx and so on. Okay, so here they are. And this is the indicial notation I just wrote down. Okay, can do the same the other way. Stress in terms of strains. You would have sigma ij equals a parameter here, lambda, I'll explain in a moment, times the trace of epsilon ij plus 2g, your shear modulus, times epsilon ij. This is indicial notation for stress ij in terms of strain ij. This is 9 equations. And here, lambda is known as the Lemay parameter, not the lame parameter, the Lemay. And here, lambda is equal to the following expression. Elastic modulus 1 plus nu on 1 minus 2 nu. All right. So that's representing the stress in terms of the strains. This is 9 equations. If you worked out all 9 equations using this formula, where I and j are going from 1 to 3, you would end up with the equations you sort of see on the right-hand side here. Okay? All right. These are, you know, the 18 equations that make up Hooke's law in 3D. You got to put the glasses on them, the 3D glasses. Make sure you can see them. All right. So what? So when we talk about generally anisotropic materials, we have to, that was just for an isotropic material, by the way. When we talk about general anisotropic materials, we're not going to have the convenience of just expressing them in terms of like one elastic modulus and one Poisson's ratio. We don't have that luxury, okay? We have to be able to express stress and strain relationships in terms of many possible elastic parameters: E1, E2, E3, nu12, nu13, G12, etc., 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 so on and so forth. Okay, so we need a way to communicate this idea of Hooke's law using not just like 2 variables, but potentially like many, many variables that define the material properties. Okay. So my point is that we need, with anisotropic materials, we need a general formula like this. Which incorporates many material constants. Okay. And to do this, the first thing we're going to do is introduce contracted notation. And let's recall that sigma ij equals sigma ji, and epsilon ij equals epsilon ji for materials which obey conservation of angular momentum. Not really important that we know that, but that's just the truth. Okay, tau xy equals tau ix. That's something you probably learned in 3005, 2004, etc. And so when we have sigma ij for I and j going from 1 to 3, usually 9 equations, but here it's actually 6, okay, because 2 of them are redundant, right? So what we're going to do is we're going to introduce a contracted indicial notation to deal with this. And that contracted indicial notation is going to say that we let sigma 1, 1 be sigma 1, Let's sigma 2, 2. Sigma 2. Sigma 3, 3. Sigma 3. Let sigma 2, 3 equals sigma 4. Sigma 1, 3 becomes sigma 5. And sigma 1, 2 become sigma 6. So then stresses are represented with sigma capital I, where capital I goes from 1 to 6. Okay. Similar for strains. Except we usually use capital J. Okay. This allows us to represent Hooke's law for any arbitrary material. Any arbitrary material. Is the following. Sigma capital I is equal to the stiffness matrix capital C Ij multiplied by epsilon j. So the strain can be represented using the compliance matrix S times the stress. This is the most general form of Hooke's law, right here. And this is known as the stiffness matrix. And Sij is also a 6x6 matrix known as the compliance matrix. I find it quite ironic that capital C is used to represent the stiffness matrix and capital S is used to represent the compliance matrix, which is kind of funny to me. These are both matrices which contain all possible values of material properties. Okay. They contain your E1s, your E2s, your E3s, your new 1, 2, your G1, 2, your etc. And they're arranged in a very specific way in that 6x6 matrices. And we're going to talk about how we construct these matrices to represent stress and strain in a composite by incorporating or thinking about things like how do we eliminate entries in this matrix for planes of symmetry, planes of isotropy, and so on and so forth. Okay, so this is kind of the first stepping stone on getting you to think about a general anisotropic material might have 36 independent material constants. Okay? It's a lot. Isotropic materials are represented with 2, E and nu. General anisotropic material represented with 36. Yikes. All right. So the lectures to come will focus on populating this particular matrix and how we deal with the symmetry conditions that we might see. That's it for today.